$13 billion, 100,000 tons of steel, 4,500 sailors, the most advanced warship ever constructed by human hands. And yet this ship sat completely motionless for 15 months. Not because of enemy fire, not because of war, but because of a single mechanical component smaller than a grown man's torso. That contradiction should stop you cold, because what it reveals about the USS Gerald R, Ford CVN-78, isn't weakness. It's something far more complicated, far more fascinating, and ultimately far more important than any combat story you've ever heard. Let's start with what this ship actually is. Commissioned on July 22nd, 2017, the USS Gerald R. Ford is the lead vessel of the Ford class, a completely new generation of American supercarriers designed from the keel up, not as an upgrade to what came before, but as a generational leap. At 1,106 feet long and displacing 100,000 tons at full load, she is physically enormous. But the numbers that matter aren't the ones about size. The Ford can execute up to 270 combat sorties per day. That's 33% more than the Nimitz-class carriers that defined American naval power for the past 4 decades. She operates with approximately 600 fewer crew members than a Nimitz-class ship, not because she's less capable, but because advanced automation has replaced entire departments of human labor. More aircraft launched, more missions flown, fewer people needed to make it happen. That is the definition of a generational leap. Now compare that directly to what China considers its crown jewel, the Liaoning, Type 001, their first operational carrier. The Liaoning displaces roughly 60,000 tons, 40% less than the Ford. Its ski jump launch system limits it to approximately 20 to 24 sorties per day under ideal conditions. Not 270, 24. That gap isn't a number. That gap is a strategic chasm that cannot be crossed with ambition alone. The reason the Ford can operate at that tempo comes down to 2 revolutionary systems that no other Navy on Earth currently possesses. The first is EMALS, the Electromagnetic Aircraft Launch System. Previous carriers used steam catapults that have been fundamentally unchanged since the 1950s. Steam catapults are violent, imprecise, and brutally hard on both airframes and pilots. EMALS uses a linear induction motor to accelerate aircraft down the deck with electronically controlled, precisely graduated force. The result: less structural stress on the aircraft, lower maintenance cycles, and the ability to launch a far wider range of aircraft weights, from a 100,000-pound E-2D Hawkeye to future unmanned combat drones, all from the same system. This isn't a better catapult. It's a different philosophy of naval aviation entirely. The second is the AN/AAG-11 Advanced Arresting Gear, which replaces the legacy hydraulic arresting system with a water twister energy-absorbing design controlled by advanced digital systems. It stops aircraft weighing up to 50,000 pounds from full landing speed to a complete halt in under 320 feet, and does it with precision that the old system was physically incapable of achieving. Powering all of this are 2 A-1B nuclear reactors, the first reactor design purpose-built specifically for aircraft carriers in American naval history. The A-1B generates 3 times the electrical output of the A-4W reactors in Nimitz-class ships. That extraordinary power surplus is what makes EMALS possible. It's what powers the dual-band radar suite combining the AN/SPY 3 multifunction radar and the AN/SPY 4-volume search radar, a system capable of simultaneously tracking targets across a 500-kilometer radius while simultaneously guiding missiles, directing air traffic, and executing electronic warfare operations. No other surface combatant in the world carries this capability. The United States Navy has stated plainly that a single CVN-78 carrier strike group can replace 3 land-based air wings in a theater of operations. 3. That isn't marketing language. That is operational planning doctrine. So here's the question that should be burning in your mind right now. If this ship is everything the Navy claims it is, why did a single mechanical failure bring the entire program to its knees just 7 months after commissioning? Type your guess in the comments. How many years did you think a ship like this would last before its first serious breakdown? If this kind of deep military analysis is what you've been looking for, hit that like button and subscribe right now. Every week we go inside the machines, the decisions, and the human stories that shape global power, and you won't find this level of detail anywhere else. Don't miss what comes next, because the real story of the Ford isn't about its power.
It's about what happened when that power suddenly went dark, and what it cost America strategically when the world's most capable warship became the world's most expensive problem. February 2018, the USS Gerald R. Ford is 7 months into operational service, conducting post-delivery sea trials off the Virginia coast. Inside the engineering spaces, buried deep below the waterline, a cluster of warning indicators begins to flash. Temperature readings on one of the main propulsion shaft lines are climbing past normal operating parameters. Vibration sensors are registering anomalies that should not exist on a brand new ship. The duty engineer picks up the phone and makes the call that will trigger one of the most expensive single repair operations in United States naval history.
The culprit is a main thrust bearing, specifically one of the 4 thrust bearings responsible for transferring the enormous rotational force generated by the Ford's nuclear-powered turbines into forward propulsion through her propeller shafts. To understand why this matters, you need to understand what a thrust bearing actually does under operational conditions. The Ford's propulsion system works like this. Her 2 A-1B nuclear reactors generate steam that drives 4 sets of Westinghouse geared turbines. Those turbines spin 4 propeller shafts, each approximately 30 inches in diameter and running nearly the full length of the ship, at flank speed over 30 knots, or roughly 56 kilometers per hour. Each shaft is transmitting tens of thousands of horsepower of torque, while simultaneously absorbing the axial thrust load generated by the massive 5-bladed propellers pushing against the water. That axial load, the force trying to drive the shaft backward into the ship, is what the thrust bearing resists. At full power, each main thrust bearing on a carrier this size is handling compressive forces equivalent to hundreds of tons of sustained pressure, continuously, in an environment of intense heat and vibration. When a bearing of this type begins to fail, it doesn't announce itself gently. It degrades rapidly, and if not caught in time, it can destroy the entire shaft line, a repair that would dwarf everything that followed.
The investigation that followed identified the failure as originating in the manufacturing process. GE Power, the contractor responsible for producing the bearing assemblies, had introduced machining errors during fabrication that created microscopic stress concentrations in the bearing surface. These imperfections were not detectable during standard acceptance inspections. They only revealed themselves under the full operational loads of sustained high-speed steaming.
This was not a design flaw in the Ford-class propulsion concept. It was a quality control failure at the production level, and it had been sitting inside the ship since before she was commissioned. What made the situation significantly worse was the scope of what the Navy had to do next. You cannot simply pull one bearing on a vessel of this complexity and call the job done. With a failure mode rooted in manufacturing process errors, the Navy had no choice but to conduct a full inspection of all 4 shaft lines, all 4 thrust bearings, all associated shaft components, all alignment measurements. The tolerance specifications for main propulsion shaft alignment on a Ford-class carrier are extraordinarily precise. Acceptable misalignment is measured in thousandths of an inch across shaft runs, spanning hundreds of feet. Every measurement had to be verified. Every component had to be evaluated. The repair contract awarded to Huntington Ingalls Industries, the same Newport News shipyard that built the Ford, ultimately carried a price tag that exceeded the initial repair estimate by approximately $100 million when full scope of work was accounted for. And while that work was being done, the strategic consequences were immediate. The Ford was removed from the Navy's deployable carrier force structure at exactly the wrong moment. With ongoing commitments in the Mediterranean, the Persian Gulf, and the Western Pacific, the U.S. Sixth Fleet was forced to extend the deployment of USS Harry S. Truman, CVN-75 by approximately 2 months to maintain carrier presence in the European theater. Sailors aboard Truman who had been expecting to return home found their schedules extended. Mission planning across 2 fleet commands had to be restructured. all of it tracing back to a flaw introduced on a factory floor in a facility that the Navy trusted to deliver components to the most exacting specifications ever demanded in naval shipbuilding. Here's the number that captures the full weight of this failure. One main thrust bearing assembly weighs less than 2 metric tons. The ship it disabled cost $13 billion to build. That ratio of 2 tons against $13 billion is not just an engineering statistic.
It is a lesson about the catastrophic leverage that single points of failure carry inside systems of maximum complexity. So who bears responsibility? The contractor who produced a defective component, or the Navy that accepted delivery of a ship without catching the flaw before commissioning? Leave your answer in the comments, because there is no clean answer. And the debate matters more than most people realize. The bearing has been identified, the damage has been assessed, the bill is being calculated. But none of that answers the hardest question yet. How do you physically move a 100,000-ton nuclear-powered warship into a dry dock, dismantle its propulsion system, and put it back together to standards that will be trusted with the lives of 4,500 sailors and the security commitments of an entire alliance? That process is more extraordinary than anything that came before it. There is exactly one dry dock on the eastern seaboard of the United States capable of holding the USS Gerald R. Ford. It is Dry Dock 12 at Newport News Shipbuilding, operated by Huntington Ingalls Industries, the same yard that built the Ford from first steel, cut in 2009. The dock measures 1,092 feet in length and 233 feet in width. When the Ford entered that structure in early 2018, she was entering the only facility in the Western Hemisphere where the work that needed to be done could actually be performed. Moving a 100,000-ton nuclear-powered warship into a dry dock is not a procedure. It is a choreography. 6 tugboats, each generating between 5,000 and 7,000 horsepower, worked in coordinated teams to maneuver the Ford into precise position above the dock's keel blocks. Positioning tolerance for this operation is measured in inches. A ship of this displacement, if settled incorrectly onto her support blocks, can suffer hull deformation, costing hundreds of millions of dollars to correct. Once the Ford was confirmed in position, over 100 million gallons of water began draining from the dock.
As the level dropped, she gradually settled her full weight onto a precisely engineered grid of hardwood keel blocks and steel bilge blocks, each positioned at structurally calculated points along the hull. Get that calculation wrong, and you damage the ship before a single repair has been made. When the dock was finally dry, over 1,000 workers from Huntington Ingalls Industries were on the job. At peak activity, the workforce reached 1,200 tradespeople working across multiple shifts, around the clock, 7 days a week. Total labor investment across the 15-month period exceeded 800,000 man-hours. If a single skilled craftsman attempted this work alone, working 8 hours a day without a day off, it would take him 274 years to complete it. The scale of coordinated human effort required to compress that into 15 months is an industrial achievement that receives almost no public attention and deserves far more. The shaft alignment work alone consumed thousands of those hours. Acceptable misalignment on the Ford's main propulsion shafts is 0.001 inches, 1/1000th of an inch, across shaft runs extending hundreds of feet through the hull. A human hair measures approximately 0.003 inches in diameter, which is sucked. The engineers achieving these tolerances were working to a standard 3 times finer than the width of a single strand of hair, using laser alignment systems that did not exist in commercial shipbuilding a generation ago. The Navy made a deliberate decision not to waste the availability. With the Ford already out of service, NAVSE engineers simultaneously addressed 2 other systems generating serious operational concern. The advanced arresting gear have been recording failure rates of approximately 46 per 10,000 arrested landings, roughly 25 times higher than the design specification of 1.8 per 10,000. Modifications to the AAG's water twister energy absorbers and digital control architecture were executed while the ship was in dock. These emails received parallel software and hardware recalibration means cycles between operational failures improved from approximately 1 failure per 240 catapult shots in early service to 1 failure per 466 shots following the upgrades, a 17-fold improvement in reliability achieved not by rebuilding the system, but by understanding it deeply enough to fix what developmental testing had missed. When the flooding cycle began and the James River water returned to the dock, the Ford rose slowly over nearly 2 full days. Engineers monitored every inch of her ascent. The ship lifted cleanly off her blocks, floated level, and rode exactly as designed. When the caisson was finally removed and the tugboats took their lines, approximately 1,200 engineers, welders, machinists, and electricians lined both sides of the dock. The Ford moved at 2 feet per minute. The full transit from inside the dock to the main river channel took over 4 hours. No one who was there described it as routine. A ship that had come in broken was leaving whole, and the people responsible knew precisely what it had taken, measured in thousandths of an inch and hundreds of thousands of hours of unrelenting professional precision. If you were the commanding officer on that bridge as the Ford cleared the dock and felt the river current for the first time in 15 months, what would be going through your mind? Tell us in the comments. The Ford is floating. The systems are upgraded. The numbers have dramatically improved. But floating and repaired is not the same as combat ready, and the real question isn't whether this ship can sail again.
It's whether it can justify its existence in a world that didn't stop threatening while it was in dry dock. October 2022, the USS Gerald R. Ford arrives in the Eastern Mediterranean. Russia's war in Ukraine has reshaped European security in ways not seen since 1945. NATO allies are watching. Adversaries are calculating.
The Ford Carrier strike group built around CVN-78, accompanied by guided missile cruiser USS Leyte, Gulf CG-55, and multiple Arleigh Burke-class destroyers, takes station in contested waters where its presence requires no translation. This was not an exercise. It was the first operational deployment of a Ford-class carrier into a genuine high-tension strategic environment. She performed without a single major system failure. That deployment answered a question critics had been asking since the Ford's early troubles became public. Was this ship actually worth what it cost? Honest analysis requires different arithmetic than most people apply. The Ford's $13.3 billion construction cost, spread across a projected 50-year service life, yields an annualized platform cost of approximately $266 million per year.
The United States currently spends an estimated $100 million to $150 million annually to operate a single mid-size overseas airbase before accounting for host nation politics, basing rights negotiations, and the diplomatic constraints of a fixed installation on foreign soil. A carrier strike group gives you a sovereign piece of American territory, moving at 30 knots, that no foreign government can evict and no adversary can locate with certainty 72 hours in advance.
The economics are not as simple as the sticker price suggests. The Navy's plan calls for 10 Ford-class carriers total, replacing aging Nimitz-class ships one by one. Each successive vessel incorporates lessons from CVN-78's operational experience. USS John F. Kennedy CVN-79, USS Enterprise CVN-80, and USS Doris Miller CVN-81 all carry specification changes driven directly by the Ford's thrust-bearing failures, EMALS reliability problems, and AAG shortfalls.
Kennedy is estimated to cost approximately $1 billion less than Ford to build savings generated by manufacturing improvements that only existed because the Ford absorbed those problems first. The lead ship didn't just suffer setbacks, it produced knowledge that will benefit the entire fleet for the next half-century. Now consider what America's primary strategic competitor is actually working with.
China's Type 003 carrier Fujian, launched in June 2022, is a genuine achievement, the first non-American carrier to incorporate electromagnetic catapult technology. But Fujian is conventionally powered. It requires refueling, requires tanker support, and its sustained at-sea endurance without logistical backing is a fraction of what the Ford maintains indefinitely on nuclear power. China has been attempting to develop a nuclear-powered carrier for over 15 years and has not yet solved it. The United States has operated nuclear-powered carriers continuously since USS Enterprise, CVN-65, commissioned in 1961, 63 years of accumulated operational knowledge that cannot be reverse engineered from satellite imagery or purchased from any supplier. Behind every strategic calculation are the human beings who carry this institution forward. The Ford's repair was executed by workers who spent 800,000 man-hours doing precision work in confined, noisy, overheated spaces, knowing that a mistake measured in thousandths of an inch could eventually cost lives at sea. That is not abstract patriotism. That is professional responsibility exercised daily by people whose names appear in no headlines and whose work will never be publicly audited, only trusted.
People ask whether aircraft carriers remain relevant in an era of hypersonic missiles and long-range precision strike. That is the wrong question. The correct question is this: in the 79 years since the end of World War II, with American carriers continuously deployed across every ocean, how many nations have chosen to attack 1-0? Not because no adversary has been capable of contemplating it,
but because the calculation of what follows the response, the escalation, the absolute finality of that decision has consistently exceeded whatever objective any attacker might hope to achieve. That is deterrence in its purest form, not a weapon that wins wars, a presence that prevents them. 50 years from now, will carriers still dominate the world's oceans, or will something we haven't yet imagined replace them entirely? Leave your answer below. The USS Gerald R. Ford left Newport News not simply as a repaired ship. She left as proof that the United States can identify a failure, absorb its full cost, fix the problem at the deepest technical level, and return stronger in capability, doctrine, and resolve. That is not a story about one vessel. That is a statement about what kind of nation builds these ships and why, after everything, the rest of the world still takes that statement seriously.